Welcome. In this session, we'll learn different classes of discrete time systems. Let's start. So there are several classes of these discrete time systems, and this classification is based upon the input-output relation in the discrete time system. So this classification that we'll learn about the discrete time system is based upon the input-output relationship of this discrete time system. So the first class of these discrete time system is the linear system. So what's a linear system? A discrete time system is said to be linear. So a discrete time system is said to be linear if the response to a weighted sum of inputs is a weighted sum of the responses of the inputs individually or separately. So a discrete time system is said to be linear if the response to a weighted sum of inputs So a discrete time system is said to be linear if the response to a weighted sum of inputs is a weighted sum of the responses of the inputs separately or individually. And this should be true for all weights and acceptable inputs. Now, what do we mean by this linear system? A system is said to be linear, or a discrete time system is said to be linear if the response to a weighted sum of inputs is a weighted sum of the responses of the inputs separately or individually for all weights and acceptable inputs. Now let's see the mathematically what do we mean by this linear system. So this is by definition. So what mathematically what do we mean by a linear system? If we denote the system, let's suppose y of n is, we say, if we use this notation, or we can say this notation, one and the same thing. I saw this in the previous class. If I use this notation, so we say this is our system. Now if we apply now different inputs, let's take the example of two inputs. Let's suppose the inputs are x1n and x2n. So let's take the example with two inputs. So we'll compute the outputs with this. So let's call those responses. When we apply individually these inputs, when we first apply x1n, let's see the output response, and let's suppose that's y1n. Similarly, when we apply x2n, we see the responses y2n. So these are the responses of these inputs individually, meaning separately, when we separately apply x1n and x2n, and we see the output response is y1n, and the response for x2n is y2n, respectively, right? And let's take the weights a1 and a2. Let's suppose the weights are a1 and a2. Now, if we apply the input to the system as weighted sum of inputs means this. Means if we weight our inputs or scale our inputs by some constant, and similarly this input by some constant, and add these inputs and apply as this input, which is the weighted sum of these inputs to the system. And if we apply this as input to the system, if we see this, if we say the output response is something like this. We say the output response is this. So what's going on here? So when we apply this as the weighted sum of inputs to the system, the output is simply the weighted sum of the responses for the individual inputs. That you can see the output response of x1n is this. You can say this is the output. Similarly, the output response is when input is x to n is h times x to n, that is here. So when you apply input as the weighted sum of inputs, the response is the weighted sum of the responses for the individual inputs, or you can write it in terms of y. Then this system is said to be linear. Then this system is said to be linear. So this is the mathematical definition of this linear system. All right. So this is how we define what's a linear system. Now you can see a linear system is one that follows the principle of superposition principle. So we can say a system is said to be linear if it follows the principle of superposition principle. So a system is said to be linear if it follows the principle of superposition principle. And we know superposition principle encompasses two properties. So a superposition principle encompasses two properties. One is called the additivity property, and another is called scaling property or homogeneity property. Homogeneity property. So a system is said to be linear if it follows the principle of superposition, and superposition principle encompasses two properties. One is additivity property, another is scaling property or homogeneity property. Now, what do you mean by additivity property? Additivity property means if you take the addition of these inputs x1n, x2n, and apply this as the input to the system, you see the response is simply the sum of the responses for individual inputs. So this is x2. So then this is following the property of additivity. So if this is true for any system, then this is following the this additivity property, meaning the system is following the additivity property. Similarly, homogeneity principle simply means you scale any input. If you scale any input by some constant. So if we scale this input by this constant k, and the response of this system is simply the constant times the response for this input, then that is following this scaling or homogeneity property. And together, additivity and homogeneity this property encompass the superposition principle, and we say if it follows both additivity and this homogeneity property, we say the system is linear. So this is another way to define what's a linear system. Now you can see from this definition of this system here, both additivity and this homogeneity property are encompassed. So whether you write it this way or this way, one and the same thing. So mathematically, whether you write it this way or this way, this one is one and the same thing. So this is how we define mathematically what's a linear system. Now examples of a linear system. Let's give you some examples of this linear system. What do you mean by what's how do we write what's a linear system? So some example. Let's suppose y of n is it operates on x of n is suppose simply x of n plus x of n minus 1 of n minus 2. So this system is said to be linear. So this is a linear system. Simply we can say y of n is y of n minus 1 x of n. So this is another example of a linear system. Similarly, the third example we can take y of n is n times x of n. So this is another example of a linear system. In other words, now remember when the system operates on x of n, remember this is the notation of the system. So when it operates on this x of n, it produces an output that is n times x of n. So what's this doing? It's simply multiplying the current sample value with the current time instant. So it is simply multiplying that. That's what the system is doing. All right. So now example, if the system is not linear, then it is non-linear. What are the examples what are the different examples of non-linear system? So if the system is not linear, then it obviously will be non-linear. Now, a few examples of this non-linear system are y of n is if n is x2 n. So this is the example of a linear system. So what is the system doing? Is simply carrying the current sample value by carrying this current sample value. Similarly, we can say y of n is sorry, this is cos. So this is the output. So this is taking cosine of the value of the current sample value. Similarly, another example can be, so when the system operates on this signal x of n, it produces an output that is takes the magnitude. Means we divide this. So what's the system doing? It is simply taking the magnitude of the current sample, then taking the exponential of that magnitude value. So this is producing e to the power of that value. So this is how we define a linear system. Linear system is one that follows the principle of superposition, and principle of superposition encompasses two properties. One is additivity property, another is homogeneity property. So if the system follows both, then and then only it is a linear system involved. Now, next is how do we check whether a system is linear or non-linear? That's the next one. So how do we check whether the system is linear? So how do we check for linearity and non-linearity? Whether the system is linear or non-linear. So that's the next one. How do you check? Now there are four steps that you can use. There's a procedure of 4 steps that you can check for this linearity, whether the system is linear. Now the 4 steps are: first, find the responses. What we do, we find the responses, means we find the individual responses y1n and y2n for the corresponding responses, for the corresponding inputs, for corresponding inputs x1n and x2. So the first step you check what's y1n and y2n when you apply x1n and x2n respectively. So this is the first step that you will see. Second step is find the sum of these responses. Take the weighted sum of these responses. In other words, what is the second response? Take the weighted sum of these individual responses. So we say what is a1 times y1n plus a2 times y2. So this is the second step. So let's name it 1. Suppose the result is named as 1. Whatever we so y1 you computed from first step, y2 also you computed from the step 1. Then you take a weighted sum. This weight a1 and a2 is any value. It can be any value, and it should be true for any value. So third step is find the output when the input is. So next step is find y1 y of n when the input is weighted input. So when the input is weighted sum of these inputs. So this is x2 and so when the input is this, what is the output? And suppose the output we term it as yn, and let's call it equation 2. Now fourth step is check or compare the results of this equation 1 and equation 2. If these two are same, means if the results of step 2 and step 3 are same, then we say these results are. So our job in this step is compare step 2 and step 3 results. If these are equal, then we say the system is linear. Let's take some examples to illustrate this. Let's give an example to illustrate this. Let me take this example. Y of n is, I will define the system like my system is doing this operation n times extra n. So that's, so let's check this. So what's the system doing? First let's learn that. Let's learn that when the system operates on this input signal, it produces n times the same input. So it produces the same input multiplied by the current sample time. So what's the first step to check for linearity? First step is compute the individual responses when the inputs were x1 and then x2. So x1n, and we see the system is simply multiplying the input by the current sample. Similarly, what will be y2n, when you apply x2n as input, it will again do the same thing. When the input is x2n, it will multiply the input by n. So the second step is take the weighted sum of these responses. Which compute this. What is a times y1n and a2 times y2n. What is this equal to? From this we can check. This is a1 times n times x1n plus a2 times n times x2. And now you can take n outside. You can say this is simply a1 x1n plus a2 x2n. Let's name this equation 1. So this is our step second. Now step third, what we do in step third, we apply the input to the system. So input to the system now is A1, means weighted sum of inputs. We apply the weighted sum of inputs to this system and see what's the output. Now what is the system doing? Simply it's multiplying the input by n. It is simply, so when the input is now this weighted sum, what will this system do? It will multiply again this input by n. Whatever is the input, it's multiplying this input by this time instant value. This is now have a look at equation 1 and equation 2. You can see these are equal. So in step 4 we compare the results in step 2 and 3, and we see these are equal. You can see the results are equal in step 2 and step 3. So you can say this is a linear system. So why is this system, when it produces the output like this, is a linear system? So this is a linear system. So this is the procedure to confirm whether the system is linear or not. So if the results in the step 1, step 2 and step 4 are not equal, then you can say this is a non-linear system. Now few more examples that you can do use as homework to check whether the system is linear or non-linear. Now the first example that you can take is y of n is suppose a times x of n plus p. Similarly, another example is y of n is, let me rewrite this. This, the output is cos of x of n. So this is second. Third example is suppose the output is x of n. So this is our. So please follow these examples at your places and check why is this system non-linear. This system seems this should be non-linear. This is obvious from the definition. It is non-linear. But why is this non-linear? Compare it with your mx plus c or max plus. Compare it with the result of this. Now, so we in this session we studied what do we mean by a linear system. Now, why are linear systems important? Why are linear systems important? Now, linear, if you go back to the definition of this linearity, what it simply says, it says that when you apply a weighted sum of inputs, the output is the weighted sum of the responses for the individual inputs. All right. So what is the implication, or what is the importance of this is that you can break any input. So what is the first implication of this linearity? So what's the first importance, the implication of this linearity is that you can break any input to arbitrary sequences or arbitrary inputs, and that we shall see how we express any this input in terms of unit sample sequences. That will be our topic for convolution, and this is the first this is the property exploited by this. This is used in this convolution sum. Means we break the any input, we break the this input signal to the unit sample sequences and take a weighted sum of those unit sample sequences. Right? And the second implication of this is exploited by transform theory. Means we express the simple this arbitrary signal as the weighted sum of complex sinusoids. We express our input sequence or any signal in terms of complex sinusoids. This is used by transform theory. Transform theory means Laplace transform, Fourier transform, Z transform. So this is used by this transform theory. So in convolution sum, we'll see how do we actually express any signal in terms of unit sample sequence or simply delta functions, and this is exploited by convolution sum. Similarly, in transform theory, we express the signal in terms of weighted sum of complex sinusoids. So this is the importance of this linearity property or simply linear systems. So that's why linear systems are very important. Let's end it here. In the next session, we'll learn what we mean by time invariance property.